Another lecture. So this week is all about knowing how to train a neural network well. So we've already learned how to build neural networks, but now we focus on how to make them actually learn effectively through proper tuning, optimization. So think of it as learning to tune an instrument. So the model's architecture might be the instrument itself, but unless it's tuned properly, it won't sound right, or in our case, it won't generalize and perform well. So this is the mathematical core of training a neural network as we've seen it before. So we are minimizing a loss function, as we said, and that's usually the L right here, where the theta right here represents all the trainable parameters, the weights and the bias, as we've discovered in previous lectures. And so the function f right here is our neural network's prediction of input xi, right? These are our inputs. And the L right here is the loss between the prediction and the true label yi, right? So this is the ground truth or the true label. So as we've seen last week in classification, we could use things like the cross entropy or the mean squared error for regression as a loss function. So unlike linear models, neural networks, they do produce non-convex loss landscapes, right? So these are filled with many local minima, and they also have some flat plateaus and some saddle points, right? So these surfaces can span thousands or millions of dimensions, right? So to navigate the space, we use what we've discovered last week, which is the gradient descent. Okay, so this one moves us in the direction of the steepest descent, right, of the loss, using the update rule, which we also discovered last week, right? And this update rule, while simple, it can behave very differently depending on the structure of the loss surface, right? And also the dynamics of the model itself, right? Especially in very deep learning architectures. So optimization is about moving through a complex loss surface, right? And how do we decide where to go, right? That's where optimizers come in, right? All of them follow the same version of the update rule, right? But the difference lies in how they compute that something, right? So we have the stochastic gradient descent, the SGD. So this one uses the raw gradient. It's simple and computationally efficient, but it can be noisy and slow to converge, especially when gradients oscillate, right? We can improve them using momentum, which improves on the simple stochastic gradient descent by smoothing out the updates, right? So it keeps a running average of the past gradients, so we don't just react to local bumps, right? So mathematically, it's like adding inertia, right? So you're rolling down the hill, not just sliding down, right? So there are actually three main variants of gradient descent. There is the batch, the stochastic, and the mini batch gradient descent, okay? So in batch gradient descent, we compute the gradient using the entire training data before taking one single step, right? So this makes the gradient direction very accurate, but it also slow and requires a lot of memory, especially for large data sets, okay? At the other extreme is stochastic gradient descent. So here we update the model after each individual training example, right? So this means frequent updates and fast iterations, but also high variance, right? So the loss may start to bounce around a lot. Now, in the middle, and the most commonly used in deep learning is mini batch gradient descent, right? So we compute gradients over a small batch of samples, typically 32, 64, or sometimes even 124. And it depends on the size of the trained data. So this one offers a good trade-off between speed and stability, right? And that works well with GPU parallelism. So in this week's assignment, you'll try to do some experiments to compare these different optimizers. There are other optimizers. There is the RMS prop, which takes a different approach. It tries to adapt the learning rate per parameter based on how large the gradients are, right? So the parameters with consistently large gradients get smaller updates, which helps with the stability of the learning. There's also ADAM. This one uses momentum and also adaptive scaling. It's the most common used optimizer in practice because it tends to converge quickly with less tuning, right? Though sometimes it doesn't always generalize better. And there are, of course, other optimizers that you should experiment with. So even the best optimizer can only take you so far if your parameters aren't tuned, right? Think of these as the dials you get to control during training. So they determine how fast and how stable and also how effectively your model learns. So the most critical one is the learning rate. It determines how large a step you take with each gradient update, right? If it's too slow, your model will crawl through training, right? Just like a baby crawls, possibly never converge, okay? If you set it too high, then your updates might overshoot, causing the loss to explode or start to oscillate wildly, right? So the next hyperparameter is also the batch size, right? This one affects both the training dynamics and the hardware efficiency. So smaller batches introduce noise into the gradient estimate. Sometimes they're helpful for escaping local minima, while larger batches, they offer smoother updates but better parallelism. They offer better parallelism, but they can overfit, right? They require more memory. Now, the number of batches is another hyperparameter to think about when fine-tuning your model. And that, as we've described it before, it simply means the number of times your model sees the full data set, right? If you train too little, your model will underfit. If you train too long, then you risk overfitting to the training data, especially without early stopping, as we've described last week. So once a model starts learning the training data really well, it may begin memorizing it. That's what we described as overfitting, right? So regularization helps prevent this by making the model work harder to generalize rather than memorize the data, right? One classic method is L2 regularization. This is also known as the weight decay. So this adds a penalty term to the loss function, as you see here, right? This is a penalty term. And this way, the penalty will grow with the size of the weights, right? So the idea is to discourage the network from learning large weight values, right? Why do we need that? Because large weights tend to make the model overly sensitive to inputs, right? Which can lead again to overfitting, okay? So we modify the loss function. We start with our original loss right here, and we add a penalty to it, right? Which is the sum of the squares of all the weight values, okay? So this term grows when the weights are large, okay? This will lead to minimizing and encourages smaller weights. Okay, so this color right here, the lambda, it lets us control how strong the regularization is. Okay, if it's too low, it has barely any effect. If it's too high, then the model will become very regularized, meaning it will become very simple and it will eventually underfit. Okay, so the other methods of regularization is dropout. So dropout is one of the most effective and widely used regularization techniques in deep learning. Okay, it's very simple. So during training, we would randomly deactivate a percentage of neurons in each layer. Okay, so if the dropout rate is 50%, okay, this is the mask we apply. So multiply each activation with the mask. So let's say we choose the dropout rate to be 50%, then half of the neurons are ignored during the forward and backward pass. So this randomness means that the model can't rely too heavily on any of the feature or path through the network. Right? It forces the network to learn more robust distributed representations, right? It's kind of like in sample learning, but within one single model. So during inference now, so we've talked about during training, right? Now during inference, which is during testing, we use all the neurons, okay? We don't deactivate any, but we have to scale them down, right? So we can match the expected value that we had during training. So for example, if you dropped out 50% of the units during training, then you have to multiply the activations by 0.5 at inference time or test time. The other regularization method is batch normalization, and it is one of the most impactful methods of regularization in deep learning. So the idea is simple. So before passing activations to the next layer, we normalize them, right? Just like we often normalize input features before sending them to the model. So given a mini batch of inputs, we compute the mean and variance of each feature dimension across that batch, and then we normalize each input by subtracting that batch's mean and by dividing by that batch's standard deviation. Okay, but we don't stop there. So after normalization, we apply two learnable parameters, the gamma and the beta, right here in the equation, right? Gamma and the beta. So these parameters allow the network to scale and shift the normalized values if needed, right? Meaning the model can still learn any transformation it needs, but from a more stable starting point. Okay, so this process has many benefits. First, it introduces what's called internal covariate shift, and that's the tendency of layer inputs to change distribution during training, and it allows for higher learning rates and faster convergence. Okay, so in practice, it adds a regularization effect. Okay. And so because the normalization depends on the specific mini batch, there's a bit of noise introduced during training, which also helps prevent overfitting. Okay. So typically it is applied right after a dense or a convolutional layer and before the nonlinearity, before the activation. So we've talked about the learning rate, right, and how important it is. And the ideal learning rate may not be the same throughout the training, okay? So in early epochs, you may want large updates, right, to escape that bad initial regions of the lost surface, right? But then later, as you approach the minimum, you want small steps, okay? You want to be more careful to avoid overshooting, right? That's where the learning rate schedules comes in. So instead of using one fixed learning rate value for the entire training process, we dynamically adjust it based on the time or performance, right? So the most basic form is step decay, which we reduce the learning rate by a constant, okay, by a constant every few epochs. That's often when the error plateaus. It doesn't change much anymore. Okay. There's also a smoother version, which is the exponential decay, where the learning rate shrinks continuously over time. Okay. We could also start with a very low learning rate and increase it gradually. Okay, so this helps when the model is sensitive to large gradients in early steps. Okay, this is common in transformers and also in CNNs. So learning rate scheduling then not only speeds up the conversions, but it can also improve the general. Next is data augmentation, which is a clever and widely used technique to help combat overfitting, especially when your data set is small. So the idea is to create synthetic training examples by transforming your existing data. So not by collecting more samples, but by generating variations, right? So in image tasks, this might involve rotating or cropping the image, right, or smoothing. But in tabular data, you could apply things like Gaussian noise to numeric features. Okay, so the key is that these augmented samples are still realistic enough to represent valid inputs. Okay, so they introduce variability that forces the model to learn more general invariant patterns rather than memorizing the training data itself. Okay, so it's important to apply these transformations only to the training set, never to the validation nor to the testing data. Okay. So underfitting, we talked last time about overfitting. Now underfitting is actually the opposite. So here the model fails to learn meaningful patterns, right? It performs really poorly even on the training set. So you will recognize underfitting when both the training and the validation loss remain really high throughout the training, okay? And your accuracy hovers near the level of 50%, okay? Near the level of simply random guessing. So this often happens when your model is too small, too regularized, as we've said, or simply too simple, okay? So sometimes even when the training is not long enough, let's say you don't use enough epochs, you don't wait for enough epochs, that also may lead to underfitting. Okay, a very low learning rate can also make the optimizer crawl, which gives the impression that the model isn't learning. So you gotta pay attention there to the learning rate. To fix underfitting, you may want to try increasing model capacity, reduce regularization, power, training longer, or changing the learning rate. Okay. Just be careful not to swing too far and end up overfitting. Another common problem when training deep neural networks is the vanishing gradient problem. So this happens when the gradients passed back through the network during training get smaller and smaller and until they're effectively zero, right? So this is especially common in deep networks with sigmoid or tangent activations. So these functions squash inputs into narrow ranges, right, as we've described in one of the lectures. So here the derivative is very small, and when backpropagation multiplies these small derivatives across many layers, the signal effectively disappears, okay, becomes zero. So as a result, all early layers in the network, they stop learning, okay, so they barely getting any signal back. So you'll notice that the loss barely changes across epochs, and sometimes the model outputs get stuck or remain uninformative. Okay, so to fix vanishing gradients, we use ReLU activations, which do not shrink the gradients in their active regions. Okay, you can also use better initializations like the He initialization, and also applying batch normalization helps to stabilize activations. Now the opposite is exploding gradients, and Here the gradient's values grow exponentially as they are propagated backwards through the network, and this usually leads to numerical instability. So you will see training loss shoot upwards or become none completely, right? So the weights grow uncontrollably, and your model may never settle into a learning phase. So this often happens in deep or recurrent networks with long propagation chains, right? Especially when the learning rate is too high or the weight initialization is not well scaled. So the solution includes reducing the learning rate, applying gradient clipping. This one limits the maximum gradient values, okay? And also using batch normalization, okay? Also proper weight initialization, like he initialization, as we said. This one helps control the gradient flow. So one of the most common confusion in deep learning is the difference between parameters and hyperparameters, right? So when we say a model's parameters are actually, these are the network, what the network learns during training, okay? So these include the weight and the bias in each layer, okay? These are updated through gradient descent, as we've said, okay? And the update is based on the loss function. Now, the hyperparameters, on the other hand, are decisions you make about the training process itself. So they're not learned. They must be set manually, and they do control how the training proceeds, right? We've seen some examples before. So these include the learning rate, the number of hidden units, the dropout rate, and so on. So you can think of them as the settings of the training model, right? So now hyperparameter tuning, it is one of the most influential parts of deep learning. You can have the right model and optimizer, but if your learning rate, for example, is off, then nothing will train well, okay? So we approach tuning systematically. So first pick the key parameters, things like the learning rate, the batch size, the regularization strength, okay? And then you explore the effect one or two at a time, okay? So changing everything at once will make it hard to know what matters, right? So things like random search has been shown to outperform other methods in high dimensional spaces. So it does cover more of the parameter space efficiently, okay? So if we talk about grid search, then that's actually a brute force kind of method of hyperparameter tuning. So you define a discrete set of values for each hyperparameter, and then you try every combination possible, okay? So it's conceptually simple and works well if you only have one or two hyperparameters to tune, okay? But it becomes extremely inefficient as you add more dimensions. You're gonna end up wasting time exploring combinations where actually one variable matters and others are irrelevant sometimes, right? But still, for small, clean tuning problems, you could use grid search. Now, instead, as we said, random search is more flexible and it offers more effective method to hyperparameter tuning, okay? So instead of exhaustively checking every point on the grid, you randomly sample combinations of hyperparameters from predefined ranges, and it's real powerful because in most tuning problems, only one or two hyperparameters actually significantly influence performance, okay? So random search has been shown to be efficient and more efficient than grid search. And it does find good configurations faster, okay? And it does cover the space better with even fewer trials, okay? So when we tune hyperparameters, what we're really doing is searching for settings, as we said, that minimize the validation loss. But the problem is that unlike typical optimization problems, we don't have a formula here for the validation loss as a function of the hyperparameters. Instead, we have to treat it as a black box, okay? We pick a configuration, train a model, evaluate it, and repeat, okay? So each guess is expensive, okay? So this is known as the black box optimization. We don't know the gradient, and we can't compute the loss without full model training. That's why random search often beats grid search, okay? So it covers more of the space with fewer trials. So the key is to find a balance, right? So when you are fine-tuning your hyperparameters, try to notice the validation performance, and if you think you are underfitting, you may want to deepen your network, add more layers. You may want to train more, so more epochs. You may want to reduce the regularization power. On the other hand, if you are overfitting, then you may want to apply the regularization methods that we've discussed, add a dropout, or simply get more data. Now, another important concept to discuss this week is the fine-tuning or the transfer learning methods. So let's start with transfer learning. So it is a method where the knowledge from a source task is where we have data is transferred to improve the performance on a target task with data set DT, right, where we have less data, right? So it is based on the insight that early layers of deep networks, especially in vision, right, or in NLP, they tend to learn general purpose features, things like edges, shapes, right? And these are often useful across tasks, right? Rather than training from scratch, we reuse a pre-trained network as a frozen feature extractor, right? So we remove its final layers and we attach a new output head suited to our destination task and train only those new layers, okay? This is both computationally efficient and data efficient. So the base model has already learned useful representations from the large-scale source data, which we now leverage to accelerate learning in a new, smaller destination task, okay? So think of it as using a pre-built foundation instead of laying bricks from scratch, okay? On the other hand, we have fine-tuning. So once you've trained a new output head on top of a frozen pre-trained model, you may want to unlock more power by allowing the base model itself to adapt. So that's what fine-tuning is about. So you gradually update the pre-trained weights to fit your specific data. So we do this carefully, right? So you first train the new layer while the base remains frozen, and then you selectively unfreeze a few layers, often just the last block, and resume training with a much smaller learning rate, okay? So this helps preserve the general knowledge the base model has, while nudging toward your target distribution. So it's especially useful when your target data differs in style or domain from the original pre-trained corpus. But fine-tuning is risky, okay? So if you train the whole network too quickly, you may actually erase useful features. This is known as the catastrophic forgetting. So you also risk overfitting if your data set is small, okay? So this table is like a map for you, right? So you compare the source and destination task, okay? So if you have similar sets, okay, then you compare the size. If the destination task is smaller, then you go for transfer learning. If you have a large destination data, then you can fine-tune it for better results. Now, if the destination and source tasks are completely different, then if the new data is small, again, you could just go for transfer learning. But then if you have enough data, it's better to fine-tune your model. So at the end, think of the reproducibility problem. It's critical, especially in hyperparameter tuning, because deep learning relies on randomness in many places, right? So think of the weight initialization, the data shuffling, the dropout. So two identical training runs can actually still produce very different results, and less randomness is controlled, right? So to get reliable experiments, you must fix the random seeds for all the libraries you're using. Okay, so in TensorFlow, in NumPy, even the Python's random module. But even that might not fully eliminate differences on GPUs, okay, due to precision and parallelism. So here you also may want to log everything. So the configuration, the training scores, the model version, and also the data set used.